Alright, so we're talking about waves. This is our last full unit that we'll have a test on. So your notes should follow along with this. You can go ahead and pause this video now, take these notes, and then listen through to me explaining them. I think that would be the best thing instead of you having to try to keep up as I'm talking. So waves are repeating disturbances that transfer energy through matter or space. A lot of the waves are going to be transferring things through matter. There are some waves, electromagnetic waves, that can transfer energy through space. Things like sound or think about other mechanical waves cannot transmit things through matter, through space, but we'll talk about that later. So waves carry energy. That energy gets transferred from one place to another. So you think about an earthquake can happen way out in the sea and the ocean, and it can transfer that energy through water and through soil, through dirt, through the Earth's crust to get, hundreds of miles away. Another example is a pebble hitting water. You can see that right here. A pebble hits in the middle of these circles. It hit right here in the middle, and then the surface of the water is disturbed, and it transfers that energy. We don't think of that as super energetic, but it is. There is energy there, and the medium is the thing that transfers that energy. So with mechanical waves, not electromagnetic, but with mechanical waves, that the medium is the thing that the energy is moving through. So in this case, it would be water. If it was an earthquake, it would be through the dirt or the Earth's crust. If it was sound, then it would be through the air. Like the way that we listen to most sound is through the air. And you've got the different parts of a wave. You got the crest at the top, the trough at the bottom. This middle line is the resting position. Think of that kind of like zero. And then how high these things are is the amplitude. How wide apart they are is the wavelength. So here we have what we're just saying, the different parts of a wave. The things that you need to know is wavelength. It would be, for example, from the top of this one to the top of the next one, or from the bottom to the bottom, or as the trough is turning into the crest right here, to the next time that the trough is turning into the crest right here. So it's any point to the next point of that same wave. So 1 is the wavelength, 2 is the trough. It's the bottom. Think about it like a feeding trough is something that animals eat out of. This looks kind of like a bowl or something that animals eat out of. Number 4 would be the crest, which is the same thing, but the opposite. It's the opposite of the trough. It's the very top of the hill or the top of the mountain. And then 3 is the amplitude. So wavelength is how is from the top of one wave, for example, the top of one wave to the top of the next. And then amplitude is how high up and down is going. So you'll see that labeled here from the top of this, the top of the wave to the resting point, or from the bottom to the resting point. The frequency, period, we're not going to use a whole lot. You can write that down, you can put that in there, but frequency is one that you're going to definitely need to know. It's the number of waves that pass through a given point in a second, and that looks different. So frequency of this is different than this. So if you imagine this wave coming towards you, if this was a wave that waves in the ocean, if you're standing right here, this is the top of one wave. The time that it would take for this to get to you and this to get to you would be a longer time period, whereas from here to here would be a shorter time period. So frequency, high frequency looks kind of like that. Low frequency would look like that. So there's a high frequency wave. This would be a low frequency wave in comparison with each other. And the period is the amount of time it takes for one wavelength to pass a given point. Again, we're not going to talk very much about that, but you do need to know frequency. Alright, so go ahead and take a second on your paper and label the parts of the wave. You can use the previous slide if you need to, but go ahead and label the different parts of the wave. Something that is not on there is nodes. So nodes are where the point of the wave meets this resting point. All right, mechanical waves. We've got two different types of waves. We've got mechanical waves and we've got electromagnetic waves. Those are the two types of waves that we're going to talk about. So mechanical waves, they transfer energy through it. They have to have a medium. That could be solids, liquids, gases. It could be the different states of matter, but it's got to be through some sort of medium. So we see this at the ocean. We see this when we're dealing with sound. I guess we don't see the sound, but we're experiencing this at the ocean with those waves. If you have a rope and somebody's holding the other end of the rope and they're pulling it up and down, that's the medium. The rope is the medium. So sound, water, seismic waves, and earthquake, that's an example of mechanical waves. Longitudinal waves, this is a type. So mechanical waves, the two categories are mechanical and electromagnetic. And then there's another two categories of waves. If you look at what they look like, I'll show you a picture real quick. This is these are the two different types actually right here. So the two different types, you can see that. So let's go backwards. Longitudinal wave is a wave that travels sideways in a line. A wave vibration is the same direction as the wave movement. So if you were to line up in single file behind 20 other people and the back person pushes the next person and you each push each other, your hand motion is going to be pushing that person. Your hands are moving side to side and the wave is moving side to side. So sound waves look like this. You can see that here. This is one example. Transverse waves. Transverse waves are what you think of if you looked at somebody actually doing the wave in a stadium, like throwing their arms up and bringing them back down, throwing their arms up, bringing them back down. As the wave goes around the stadium, your hands will be going up and down, but the wave will actually be transferring left and right. It'll be transferring sideways. So transverse waves, waves that goes up and down. It looks like a traditional wave at the beach or something like that. Examples, guitar strings. If you strum a guitar string, it vibrates back and forth sideways. So recap, see if you can go ahead and pause the video here, see if you can identify all of these and see identify which ones go where. And if you can't, then double back and look at your notes and see which ones are which. Alright, so let's talk about mediums. Like I've said a couple times, all mechanical waves have to have a medium to travel through. They have to have a solid, liquid, or gas. If, let's say, you took your helmet off in outer space and you screamed really, really loud, nobody would hear you. If they were 2 feet away from you, you could scream as loud as you wanted, and nobody will hear you because sound requires a medium, things to push against each other. Sound can go through solids, liquids, or gases, but it has to have some kind of medium. And those are the three types of medium: solids, liquids, or gases. Each of them affect the speed of the wave. So the fastest medium for waves to go through is solids because the objects are close together. The previous example that I gave where somebody is in front of you in a line, there's a whole line in front of you. If you were, awkwardly close to each other, pushing on them, it would move if you push the person in front of you and they push the next person, that could go through the line very, very quickly because you don't have far to move. If I put 10 feet in between each of you, so you're each individually spread out, that will take a lot longer for you to go push the next person. And so that's what a solid is something that is the material is closer together. Gases, they are going to be spread out a little bit more. And so the gases is the slowest form of medium for waves to go through. Solids are the fastest. And so you need to know these relationships. As energy increases, amplitude increases. This is with sound waves and similar waves. As energy increases, the amplitude increases. You can see that however high that wave is going, up really high or down very low, that means it's going to be, if this was sound, it would be louder. So the more energy there is, the higher those are. So the higher these waves, this amplitude is, the more energy there is. And high energy creates high frequency. So a line that looks like this is going to have more energy than a line that looks like this. And I think you can think about that with frequency. If you hear somebody screaming really, really loud in like a TV show, a cartoon or something, the glass can break. And a high frequency wave can break glass. Low frequency wave would take, it's less likely to break the glass. And so when the frequency increases, wavelength increases. As frequency increases, wavelength decreases. They have an opposite relationship. So frequency, high frequency looks like this. Again, high frequency, low frequency. So if it's high frequency, here's the wavelength. This is one wavelength. Whereas this is one wavelength. So this one has, the one at top has a high frequency and a small wavelength. This one has a low frequency and a very high wavelength. They're opposites. See the same thing that we just talked about right here. You can pause that and look at these. Compare the wavelength, compare the frequency, which one has a high frequency, which one has low, which one has a long wavelength or a short wavelength, and which one's high energy and low energy. On this one, the amplitude is the same for both of these. These are about the same. They have about the same amplitude from here to here. It's about the same. So the amplitude is the same. If the wavelength gets shorter, then the energy is going to be more. And this is what a sound wave looks like. They all start from a vibration. That's the disturbance that causes it, is a vibration. And it uses, sound waves are longitudinal waves like we talked about already. This is the wavelength. If you were to draw this out, it would be similar to these compressions or rarefactions. Refractions is right here. So you have a compression. That would look like, that would kind of be, if you wanted to think about it this way, where there's ebb and a flow. I guess maybe think about it like that. There's ebb and a flow. This is where there's very little compression. There's where there's a lot of compression. And that would be similar to these ups and these downs here. Alright, so sound waves. We mentioned some of this. The loudness, how loud a sound is, depends on the amplitude of the waves. So for this one, high amplitude is going to be a drastic difference between these places where there's a lot of compression and not a lot of compression. And so this is going to be a high amplitude because there's a drastic difference. You can tell the difference between this section to this section. Over down here, this is still compression, but it's not as compressed. It's not as compressed. There's not a difference as big of a difference between this section and this section. So this is a lower amplitude. If you were to think about this in view of a wave that we typically look at, it would look like this versus this. There's not as drastic. It's not as drastic of a change from here to here like it is from here to here. So high amplitude, greater amplitude is going to be where they're smushed together tighter and looser over here. Alright, so pitch is also determined by the wavelength. This frequency, I think you may be familiar with that frequency. This shorter wavelength is going to have a high frequency, and this longer wavelength is going to have a low frequency. We've got the speed of sound waves. We've already talked about this. Solids transmit them quickly. Gases are much slower. You can pause this and take some of these notes if you need to fill in the blanks. And the Doppler effect. We'll preview this here. We'll talk about it at another time. But Doppler effect is just a moving object moving towards you is going to sound higher pitched than it will as it's moving away from you. As it's moving away from you, it's going to be lower pitched. And you know this inherently when you hear an ambulance. You've noticed that higher pitched means it's coming towards you, and lower pitched means it's going away from you. You can see that on here.